Signal processing is an area of systems engineering, electrical engineering and applied mathematics that deals with operations on or analysis of analog as well as digitized signals, representing time-varying or spatially varying physical quantities. Signals of interest can include sound, electromagnetic radiation, images, and sensor readings, for example biological measurements such as electrocardiograms, control system signals, telecommunication transmission signals, and many others. History. According to Alan V. Oppenheim and Ronald W. Schaefer, the principles of signal processing can be found in the classical numerical analysis techniques of the 17th century. Oppenheim and Schaefer further state that the digitalization, or digital refinement of these techniques can be found in the digital control systems of the 1940s and 1950s. Application fields of signal processing: audio signal processing for electrical signals representing sound, such as speech or music, speech signal processing for processing and interpreting spoken words, image processing and digital cameras, computers and various imaging systems, video processing for interpreting moving pictures, wireless communication, waveform generation, demodulation, filtering, equalization, control systems, array processing for processing signals from arrays of sensors, seismology, financial signal processing analyzing financial data using signal processing techniques, especially for prediction purposes. Feature extraction, such as image understanding and speech recognition. Quality improvement, such as noise reduction, image enhancement, and echo cancellation. Source coding, including audio compression, image compression, and video compression. In communication systems, signal processing may occur at OSI Layer 1 in the 7-layer OSI model, the physical layer. OSI Layer 6, the presentation layer. Typical devices: filters for example analog or digital, samplers and analog to digital converters for signal acquisition and reconstruction, which involves measuring a physical signal, storing or transferring it as digital signal, and possibly later rebuilding the original signal or an approximation thereof. Signal compressors, digital signal processors, mathematical methods applied in signal processing, differential equations, difference equations, transform theory, time-frequency analysis for processing non-stationary signals, spectral estimation for determining the spectral content of a time series, statistical signal processing analyzing and extracting information from signals and noise based on their stochastic properties, linear time invariant system theory, and transform theory, system identification and classification, calculus, vector spaces and linear algebra, functional analysis, probability and stochastic processes, detection theory, estimation theory, optimization, numerical methods, time series, data mining for statistical analysis of relations between large quantities of variables, to extract previously unknown interesting patterns, categories of signal processing, analog signal processing. Analog signal processing is for signals that have not been digitized, as in legacy radio, telephone, radar, and television systems. This involves linear electronic circuits as well as non-linear ones. The former are, for instance, passive filters, active filters, additive mixers, integrators and delay lines. Non-linear circuits include companders, multiplicators, voltage-controlled filters, voltage-controlled oscillators and phase-lock loops. Discrete time signal processing. Discrete time signal processing is for sampled signals, defined only at discrete points in time, and as such are quantized in time, but not in magnitude. Analog discrete time signal processing is a technology based on electronic devices such as sample and hold circuits, analog time division multiplexers, analog delay lines and analog feedback shift registers. This technology was a predecessor of digital signal processing, and is still used in advanced processing of gigahertz signals. The concept of discrete time signal processing also refers to a theoretical discipline that establishes a mathematical basis for digital signal processing, without taking quantization error into consideration. Digital signal processing. Digital signal processing is the processing of digitized discrete time-sampled signals. Processing is done by general-purpose computers or by digital circuits such as ASICs, field programmable gate arrays or specialized digital signal processors. Typical arithmetical operations include fixed point and floating point, real-valued and complex-valued, multiplication and addition. Other typical operations supported by the hardware are circular buffers and lookup tables. Examples of algorithms are the fast Fourier transform, finite impulse response filter, infinite impulse response filter, and adaptive filters such as the Wiener and Kalman filters. Nonlinear signal processing. Nonlinear signal processing involves the analysis and processing of signals produced from nonlinear systems and can be in the time, frequency, or spatiotemporal domains. Nonlinear systems can produce highly complex behaviors including bifurcations, chaos, harmonics, and subharmonics which cannot be produced or analyzed using linear methods. See also, audio filter, delay, dynamic range compression, companding, limiting, and noise gating, reverberation, notes and references. External links, Signal Processing for Communications, a free online textbook by Paolo Prandini and Martin Vetterli, Scientists and Engineers Guide to Digital Signal Processing, a free online textbook by Stephen Smith, Signal Processing Techniques for Determining Power Plant Characteristics, the IEEE Signal Processing Society.